Hormones, hormones, hormones everywhere. Hormones, 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 hormones everywhere. You know, there's hormones in the pancreas to help digest our food. And there's glucocorticoids that make us feel real good. Hormones in the kidney, and there's hormones in the brain. Hormones help us sleep at night and really stand the pain. Hormones from the thyroid for our metabolic rates. And gonadotropins, they help women ovulate. There's feedback loops and circuits that are beautiful to watch. And in this course, we'll study them a lot, but not too much. Hormones, hormones, hormones here and there. Hormones, 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 hormones everywhere. Hormones, 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 hormones everywhere. Welcome to Hormone Circuits, Lecture 3, Insulin and Glucose. We're celebrating 100 years to the discovery of insulin, life-saving hormone, 1921, University of Toronto, Banting and Best, isolate a hormone that was life-saving because up to then, about 1 out of every 100 children would get a mysterious disease where they would become very, very thin and die, and there was nothing to do about it. Now we call it type 1 diabetes. And this disease is cured when you inject insulin, because this disease has to do with the loss of insulin. And that's why this amazing discovery was part of the heroic age, let's say, in the 20th century of discovering hormones. Leptin, by the way, was discovered in 1994, one of the last hormones to be discovered. Hormone circuit. So we're celebrating today, and we want to understand the glucose-insulin circuit, and this circuit will walk with us for the next two lectures after this one, because it has a lot of basic principles that appear in other physiological circuits and are beautiful to watch. So that's our plan for today. And let's take a nice deep sigh of relief. Welcome, breath. And here in the middle it says review. So up to now in the course, we had 2 lectures on the leptin circuit that regulates our weight and, more precisely, amount of fat in our body. The more fat we have, the more leptin is secreted. Leptin acts on the brain to reduce food-seeking activity, so we eat less. More fat, more leptin, we eat less, therefore less fat. And we analyzed that feedback loop in terms of a phase portrait where we plotted the diet line, how much you get, your fat you have if you keep a steady state diet with a certain amount of food, and the appetite line, which is given a certain fat level, how much you'll eat the next day. The intersection of those 2 lines is the set point, and we saw that the set point depends on physiological parameters that we could define. For example, how much energy is expended, gamma E, or alpha F, the exchange rate of a gram of food to gram of fat, and those parameters, or leptin resistance, KL, or Umax, the satiety level, and changing those parameters move the set point. And that's why people can have very different set points. The percent fat among adults can range by a factor of 3 or 4, up to, let's say, 40%, from, let's say, 15%. It's lower in children. So there's a large range. And also food intake, there's a large range. And leptin levels, there's at least a 20-fold range among healthy adults. And that means that this set point helps us regulate our own fat level, maybe over decades, but it's different between different people. Today, we're going to talk about a circuit that's much more precise than that. We're going to talk about a circuit that keeps your blood level, the sugar level, glucose, this molecule with 6 carbons, the primary fuel for many organs in our body, like the brain. It keeps it, you take different healthy people, you'll see that they have almost the same concentration of blood glucose. This concentration of blood glucose is around 5 millimolar, on the order of 90 milligrams per deciliter. That's another unit used more in Europe. Millimolar means a molar is is the Avogadro number of molecules in a liter. So millimolar is 610 to the 21 molecules. Milli is 1,000 in a liter. And 5 millimolar is a concentration of glucose in the blood. And why is it so important to keep in 5 millimolar? What do I mean? I mean, if you have 5.6 millimolar, that already clinically means you have prediabetes and you have to watch out what you eat and start exercising. And if you cross another threshold that I'm blacking out on now, luckily I have my lecture notes and you will too. Yeah. I'm trying to say that it has to be, glucose has to be very constant, and it's very important because if you have above 7 millimolar, 6.9, you have diabetes, this type 2 diabetes, a disease that is an epidemic. It's tripled since 1975. It's very bad. Why? Because if glucose levels are high, chronically high, it's not such a big difference, right, between 5 millimolar. I mean, 5 millimolar is when you're fasting, when you wake up, and 7 millimolar. It's not such a big difference. But if you have the high sugar chronically, it starts sticking to different parts of where it shouldn't, is particularly to blood vessels, small blood vessels. And over time, this causes symptoms like blindness in the eye, like heart disease, kidney disease, where those little capillaries get damaged, and organ amputation. So diabetes is a very, very common and very deadly disease. 1 out of $7 spent on health in the world is spent on diabetes. Huge type 2 diabetes, a huge, huge problem. On the other hand, you don't want glucose to go below 5 millimolar. If you go below 3, you have what's called hypoglycemia. So hypoglycemia, which hypo means too low, and glycemia comes from the word glucose, too low glucose. In this hormone course, hormone people have to say hyper. Hypothyroidism, too low thyroid hormones. Hyperthyroidism, too high. Hypoglycemia, too low glucose. Hyperglycemia, too high glucose. So hyper and hypo will be our friends. And then, of course, there's normoglycemia, where you're in the healthy range. You know, in your blood test, the glucose blood test, if you're in the normal range, that's called normoglycemia. And so if you have hypoglycemia below 3 millimolar, your brain doesn't have enough fuel, you can faint. The body might switch to ketone bodies, a different fuel, which can cause blood acidity, give you ketoacidosis, which can be fatal. That's why a lot of people with diabetes can't control their glucose, have a problem in the circuit. They need to carry some candy in their pocket. So when they have hypoglycemia, they eat it. Otherwise, they can get in trouble from this hypoglycemia. It can be fatal. So think about it. You need to keep glucose in your blood in a tight range, right? Between, let's say, 4 and 5.6 millimolar. That's pretty tight, despite the fact that you're eating all the time. And when you eat, your blood glucose can go up to 10 millimolar. You have to get rid of it because you don't want it to be high for long periods of time. And you don't want it to get too low. So you need a circuit that can quickly respond to glucose and keep it in a tight range. And that's a difference from our weight set point that we saw could vary by a factor of 3, 4 between different people, etc. So we need a new circuit with new principles. And just to illustrate, it's not only that the steady state fasting level when you wake up, you haven't eaten, 5 millimolar glucose is so constant between different individuals. It's also the dynamics, that is to say, how it rises and falls after a defined glucose input that's also very constant between people. So not only the steady state, but the entire dynamics are constant to a good approximation between healthy people. One way to see that is to think of a very common clinical test. People who have been pregnant, women who have been pregnant all had to do this test. It's called the glucose tolerance test. Or by its nickname, GTT. And in this test, you drink 75 grams of glucose. Pretty disgusting. And then there's a blood test that measures your blood glucose after an hour or 2 hours. Let's say after 2 hours. Right? So here I'm going to plot glucose concentration, and here is time. Okay, so glucose concentration, 5 millimolar is your fasting glucose concentration. And at this point, time t equals 0, you drink 75 grams of glucose. And because you drink it, it goes into your intestine, it's absorbed into the blood, and your blood glucose level rises. The intestine is really good at absorbing glucose. It's a sugar that we love to absorb. There's other sugars, fructose, etc., that are broken down during metabolism into glucose. Some gut bacteria and in the body, etc. So glucose is like a common denominator currency of how much carbohydrates you've eaten, let's say. So what happens with time, so 1 hour, 2 hours, so it rises, it reaches a peak, let's say 10. And then by 2 hours, it's back. Maybe there's a little undershoot. This is for healthy. Just to show you how sensitive this is, if you have different dynamics, you're diagnosed with diabetes. Okay, so some people with diabetes even have kind of normal glucose levels. I mean, a lot of people with diabetes have, let's say, this is their baseline, so that you don't need the glucose tolerance test. But some people with diabetes have pretty normal, but it looks like this. Okay? And if you are above 11 millimolar at 2 hours, it's also a criterion to say you have type 2 diabetes or diabetes. So you can either have above 7 here in the fasting, or above 11, 2 hours after the glucose tolerance test. Those are clinical criteria for diabetes. And people with pre-diabetes are somewhere in the middle. Yeah, so fasting glucose above 5.6 millimolar, it's called pre-diabetes, and above 6.9 is diabetes. So that's how tight it has to be. The dynamics. So we need a circuit that controls not only the steady state, but the entire dynamics, and take into account the huge difference between people, because a lot of obese people, we'll see, have absolutely normal glucose dynamics. So different parameters, physiological parameters, and keep something so precise. This precision, there's a word for it in biology, homeostasis, which means keeping the body within the different parts of the different chemicals in the body, different functions of the body, within a tight range where the body can function properly. This is homeostasis. This circuit performs homeostasis on glucose. But I just want to say there's two kinds of diabetes. Hundreds of millions of people in the world suffer from diabetes. 90% of them is what's called type 2 diabetes, where you're, I'm getting ahead of myself. I have to explain a little bit more in order to explain what I mean by these two kinds of diabetes, type 1 and type 2. I'm getting ahead of myself, so I'm going to come back and take a nice deep sigh of relief. How does this circuit work, right? so the hormone that keeps glucose, gives it 5 millimolar and does all this work is called insulin. Insulin, 100 years to the discovery of insulin. Insulin is a polypeptide. It's a small piece of protein that, like all hormones, is made by one organ, flows in the blood, and reaches other organs and instructs them what to do. So the way this works is following. And follows. Oh, I should say, I forgot to say, exercise 1 is available in this course, and it's due in 2 weeks. This exercise is designed to be enjoyable. It has parts where you have to think about the leptin and fat circuit, and it has even a simulation, a numerical simulation, where the computer will tell you what happens to the fat over time. That should be like an introduction to the simulations we'll use more and more in this course. And then also a little mathematical calculation you can do as a warm-up exercise. So I think it'll give you a taste of the exercises in this course, and also help you think again about the materials. There's also the lecture notes available where you can read basically every word I say and a little bit more bonus material that I added there with some figures, etc. So please take a look at the lecture notes. How does the circuit work? So we talked about insulin, and the idea is very simple. Insulin it works like this. What insulin does is help cells take glucose away from the blood and store it into the cells. So insulin reduces glucose blood level. And the way it works is, if I draw here for you this is a blood vessel. And I opened up a little window here. And near the blood vessel here is a cell. There's the nucleus. Cells, by the way, are typically 10 microns in size. And we're talking about blood vessels come in different sizes. The smallest ones, capillaries, are similar to this 10 micron size, and also made of a single layer of blood cells that are like a cylinder, and the blood flows in here. So inside the blood, we have the glucose, this tiny little molecule, of course, much smaller than microns. This molecule is on the order of 1/10 of a nanometer. It's a tiny little molecule here. And it's flowing in the blood. And now it can't go into the cells because the membrane of the cells is a kind of a fatty material that doesn't let a sugar molecule go in. It needs a special transporter. That's a protein that's like a pump. Now these transporters are hidden inside the cell in little vesicles, and they're not on the cell surface, so they can't import the glucose. That's glucose can't go in. In order to go in, it needs insulin. So I'm going to draw here insulin. And when this hormone is in the blood, it binds the receptor, the insulin receptor. And when hormone binds the insulin receptor, there's different signaling pathways inside the cell, changes inside the cell, that makes these transporter go to the cell membrane. So those of you new to biology, these things are like little machines designed to do things like that, to have these vesicles with the transporter fuse with the cell membrane, and transport goes in. And I was amazed coming from physics to biology, that's how it works. But that's what cells can do. And when the transporter is here, glucose goes into the cell and therefore is removed from the blood. And that's how insulin removes glucose from the blood. So I'm going to ask you now to chat some questions. I'm really interested to see if I'm explaining myself. chat some questions for me. I'm not going to continue until somebody chats a question, so here's your chance to contribute to the class. Nobody's chatted yet? Oh, great. Why doesn't cell put glucose transporter at all time anyway? So the question is, why doesn't this transporter sit in the cell membrane at all times? So if it did, it could import glucose all the time. And the body, this is a very important point, uses insulin to control when cells can take up the glucose. And there are situations I'll talk about later where the body doesn't want the cells to take up glucose. It wants the glucose to stay in the blood. And for example, if you're pregnant and you want that glucose to go to the baby, to the embryo, you maybe want to prevent the cells from taking up the glucose. Another example is infection. If your immune system now needs this glucose, the immune system in the blood to work, you prevent the body from taking up glucose. So insulin and all this pathway is a great way for the body to tune where the glucose is going. Did that make sense to you? And did I answer your question? You can say yes, no. All right. We'll later see how insulin resistance is a knob used by the body to tune that. All right. So the feedback loop that we're talking about has this part where if you eat a meal, you have glucose in the blood, but then there's this hormone insulin that removes glucose from the blood. But insulin, to complete this feedback loop, I want to tell you that insulin is only made when there's glucose, high levels of glucose in the blood. So we're going to see that insulin is made when there's high amounts of glucose in the blood. So more glucose, more insulin, less glucose. And where is insulin made? So here I drew a human body, like schematically, and I want to point your attention to this organ here called the pancreas. It's like a dollar-sized, dollar bill-shaped organ, about here. And that's the organ that makes insulin. This organ makes a lot of other things, like digestive enzymes that help you digest your food. That's let's say 99% of what this organ does. And there's 10%, 1% of the cells that make insulin. And if I zoom in here on the pancreas, I'll see that there are these collections of cells called islets. And these collections of cells, they have about 3,000 cells, of which about 2,000 are called beta cells. Beta cells. And it's the beta cells that make insulin when there's glucose. These islets have a few other cell types. There's alpha cells that make another hormone called glucagon that helps you when you have too low glucose and makes the liver make more glucose, glucagon. And it has other cells for other hormones that I'm not going to discuss. I'm going to keep things simple. There's many, many details. And tell you what's essential to understand the principles. Right, so we have the beta cells making insulin when glucose is around. And I just want to say also that the cells that take up insulin are not all the cells in the body. The cells that take up insulin, cells with this transporter story, these cells are muscle and fat cells. They take up glucose. They convert it into glycogen, which is like a storage molecule. And then they use it when you need energy. Like if you run, sprint, your muscle is burning that glycogen in order to give itself energy. So, all right. So we're going to concentrate on this circuit, and now I can tell you what those diseases are. So 90% of people with diabetes have what's called type 2 diabetes. And by the way, in this course, we're going to explain why, what's going on? What's going on in this circuit? What happens that gives you type 2 diabetes where you're not making enough insulin to remove your glucose? You're not making enough insulin, and therefore you have this problem of high insulin, high glucose that doesn't go away quickly. It's a problem. And then there's another mysterious disease called type 1 diabetes. That's what I said, that 1% of the children got a mysterious disease where they got very, very thin and died. And when you inject insulin, they're cured. Those kids don't have beta cells. So they don't have insulin. They don't have insulin. Insulin can't go into the cells because the transporter is, and the cells basically starve. Even though the body is full of glucose, the cells starve. And that's what happens in type 1 diabetes. And once you take the insulin injection, you're cured, but too much insulin can give you hypoglycemia. And so even this cure is very dangerous. Yeah, so people with type 1 diabetes today are alive, those kids are alive, but there's higher risk for heart disease and all kinds of complications. Even though now there's little automatic pumps that can basically recapitulate this circuit, read the glucose and secrete insulin. That's actually only this year, I think there's fully automated pumps without human intervention because it's so difficult actually to do it, and we'll discuss why. And I really appreciate more questions by chat. Unless, I can't believe them crystal clear and there's no questions. All right, so we said that there's a situation of pre-diabetes, and then there's full-blown diabetes. You're not making enough insulin. And there's the type 1 diabetes where you lose beta cells. We're going to explain, and actually type 1 diabetes is very mysterious. It's not just you lose your beta cells. That doesn't happen. It's that at a certain age, let's say age 11, the body immune system starts killing your own beta cells. Can you believe it? Your own body is attacking your beta cells. T cells are supposed to kill virus-infected cells. Kill the beta cells specifically. They don't kill the alpha cells that make glucagon. They don't kill it. They go after your beta cells. And they kill them so effectively that you don't make insulin anymore. And why the body attacks itself is a huge question. And it's also a question we're going to address in this course, because a lot of hormone circuits have this problem. A famous one is the thyroid, where many people have the body attacks the thyroid and destroys it, and you need to take thyroid supplement, thyroxine, all your life, basically. So why does that happen? And why are some organs attacked and not others? We're going to cover that in this course too. So there's a lot to understand. The next step is to understand this circuit and understand, can it really explain the glucose tolerance test, how things are so specific and precise? Because what we did so far is a verbal description that's taught to most biologists and most clinicians. And we want to go beyond that to see what can be gained by mathematical models, and we'll see that a lot can be gained. Early one morning, the sun was shining. I was sleeping in, wondering if my beta cells were still making insulin. What with the threefold rise of diabetes, yeah, and type 2 as well, all over this crazy old world, you never can tell. Yeah, and I was standing on the side of the road, rain falling down on my shoes, heading out for the clinic. God knows I paid some dues getting through, tangled up in glucose. We both had type 1 diabetes with an insulin syringe. Split up on a dark, sad night after an eating binge. I felt my glucose rise, my world began to fade away. Heard her say over my shoulder, We'll meet again someday on the avenue, tangled up in glucose. Rode that car out as far as we could, abandoned it out west. Okay. So what's going to happen with this couple with type 1 diabetes? Maybe we'll see later. But for now, let's get mathematical. So I drew here, you see muscle, and I try to draw fat and muscle, which are what takes up the glucose. The liver, this is the liver, also plays a role. When we're sleeping and we're not eating, liver makes glucose. It makes it out of breaking down those glycogen molecules I talked about where it's stored glucose, so it breaks it down. That lasts about half the night, and then it switches to making glucose from amino acids that come from muscles. So muscles break down a little bit, give us amino acids, and that carries us the other half of the night. So the liver is working to make glucose. Yeah, and that's another. So that's why I drew here the pancreas, the liver, which is like a 1 kilo organ, just also in this region, and the fat and muscle have the role to store glucose and take it away from the blood under control of insulin. Maybe I should also draw the brain, which is the main client for insulin. It's using glucose. It's using glucose as a main fuel source, and also red blood cells and a lot of other organs. They rely on glucose. Other organs can use other things too. All right. So I think we're ready to just erase also this body here. So we can have a space to operate. Oh, and there's a question. There is a broad knowledge today about the mechanism of how the brain knows glucose content in the blood. So how does the brain know glucose in the blood? That's a question. The brain, yeah. So I should say that the brain, when we're thinking of eating, or before we eat, or as we eat, the brain sends signals to beta cells through nerves and make them start to secrete insulin before we eat. And another pathway is when the food is in our stomach, there's hormones secreted from the gut, like GLP-1, that tells food is on the way, and they enhance the secretion of insulin. They're called incretins. All these are ways for the body to anticipate eating. So those are important. And I don't know, there are, in fact, leptin-related neurons, POMC in the blood that have to do with glucose regulation. Those circuits are being mapped out right now. But the main control is through this feedback loop as far as we're gonna consider. If we reach prediabetes, can we go back to normal? Yeah, from prediabetes, you can go back to normal. Even from type 2 diabetes, you can go back from normal. All it takes is, for most people, is exercise and nutrition. That's very hard for most people to do, but we'll understand why. It's a kind of a reversible disease until very late stages where you lose all your beta cells, also in type 2 diabetes. We'll get to that. It's reversible disease, yeah. That's actually very hopeful. Thanks for telling me. It's one of those reversible diseases. Maybe it's worse to have hypoglycemia, and so the body created this mechanism. Hypoglycemia. Indeed, a big danger is hypoglycemia. You don't want the body to have too low glucose, and that's one reason why you don't want those transporters there all the time, if I understand you correct. A good point. You don't want to remove glucose from the blood, so thanks for that comment. Thanks. Okay, great. So you see, there's good ways to think why these mechanisms evolve, right? And when there's low glucose, there's a whole special hormone called glucagon, secreted from the alpha cells in the islets, that makes the liver make more glucose. So liver production and meals are the input to this circuit. We're going to call them M, this input. G is concentration of glucose. B is the amount of beta cell mass. I is insulin, and usually it's measured in units of hormone action. There's a way to convert them to nanograms per milliliter, etc. Okay, so what are we going to do next? We're going to consider the circuit, enjoy the circuit. Did I do everything? Yeah. Great. Okay, so I'm going to write down the model equations and we analyze them and see. Our goal is, does this story that I just told you explain the tight regulation of steady-state glucose and glucose dynamics? Is this enough, or do we need to add more? Because we want to go beyond the textbook description and what you see, what you read in Wikipedia and doctors learn in medical school and endocrinologists think about, etc. So we're going to write an equation for the rate of change of glucose. Which is equal to production minus removal, right? Yeah. So rate of change of glucose is production. So this is liver production, and the meals, this, all this M. Yeah. And then we need removal. So, you know, we usually have this term for removal rate. That gives you a certain probability per unit time for glucose molecule to be removed. And that's great. And we can say that, for instance, at steady state means glucose isn't changing anymore. So in order to solve what G steady state is, I move it to the other side and divide by alpha. So the more glucose production I have in the liver, the more glucose I have. And the faster it's removed, the bigger alpha is, the less glucose I have. Units of 1 over time. So you can say if we have a meal, so we have a rise in production. In this equation, glucose is also going to rise and reach a new steady state. Okay? And if I stop the meal, glucose is going to fall. The bigger alpha is, the faster it's going to fall, and also the faster it's going to rise. So why not make removal rate really, really large? Because then I'm going to have to make production rate really, really large. That's like the question, why don't we have to transport it into the cell all the time? Because if we did, the liver would have to work hard all night to make glucose, which is taking into the cells, and that's not good. That's why we want to regulate this removal rate. We want to make alpha depend on insulin, so that we want to make the removal rate big only when glucose is around. Yeah, our cameraman has a coughing fit today, so we wish him a lot of health. So we might make the removal rate proportional to insulin. The bigger insulin, the more removal. And that's those mechanism where the transporters go to the cell surface and glucose is removed. So I'm going to write here S times I. S is called insulin sensitivity. It's the removal rate per unit of insulin. Right? And this is going to be a very important parameter. Insulin sensitivity. So with insulin, what this does is that when there's glucose around, insulin levels rise because of the beta cells make insulin, and therefore removal rate is faster, and you get rid of the insulin, and you have less insulin because of the removal rate is high. You have less maximum glucose because insulin is removing it. Okay, I know this was fast. I'll show it to you soon in another way. So this is going to be our equation for glucose production and removal. And now, in order to close the loop, we need an equation for insulin. That's the other variable in this story. So the rate of change in insulin is going to be production minus removal, right? As always. So our production is going to be, I'll start with removal. Removal is just normal removal rate, insulin removal rate. It's removed, it has units of 1 over time. It's around, the insulin half-life is around 5 minutes. Log 2, last lecture I told you, it's log 2 over the removal parameter. So insulin is removed quite quickly. By the way, insulin is removed like this. It goes from the pancreas straight to the liver, and it's degraded in the liver, and let's say 80%, and the remaining 20% go to the circulation, to the muscle and the fat, and then that gets removed in the kidney, which filters the blood into the urine. So altogether, insulin has a 5-minute half-life, which is much faster, by the way, than the removal rate of glucose, which, as we saw in the glucose tolerance test, can take an hour. So we have our removal rate, and then we have the production rate. So production rate, it's made by beta cells, right? So we're going to write here Q beta. Q is the maximum production per beta cell. And this is the mass of beta cells. So if this was true, we'd have maximal production all the time. But beta cells are smart. They measure glucose, and that tells them how much insulin to secrete. And so the way they do that, we're going to write down here as a function f of g, which is the more glucose, the more secretion. I'm just going to plot what f of g looks like. Here we have glucose. Here is this control function. And it looks like this. The more glucose, the more insulin. Its halfway point is around 8 millimolar. This is around 5 millimolar. So around 5 millimolar, it starts rising. At 8 millimolar, it reaches halfway and then saturates out around 11 millimolar. And this, as we saw last time, can be described very well by what's called the Hill function, where f of g is g divided by k is g. And this comes from biochemical theory. You can write down, and that's found in the appendix of the lecture notes. And this k is the halfway point, about 8 millimolar. And n is about 2 for people. So it's a kind of a, n controls the steepness here. And that comes from the way these beta cells are made. They actually take in glucose. There's an enzyme that prevents glucose from leaving the cell. It phosphorylates. It makes a charge. That's called glucokinase. It takes the glucose, makes a charge. Glucose can't go out. This glucokinase has a halfway saturation point of 8 millimolar, and it's what determines this sensing. And then glucose goes into the cell, which breaks it down into ATP and carbon. That's called glycolysis. And that pathway works very hard in beta cells. And it's also used to measure glucose concentration. And that ATP gets converted into a signal that tells the cell how much insulin to secrete through a ion pump-based mechanism. That's details you can see in the lecture notes, but that's what's important for us now. So we have our equations. But those equations, I mean, what do we do with them, right? How can we understand them? And I want to equip you with ways to understand these equations. But if you put this on the computer, you can basically simulate a glucose tolerance test. So you give a little bit more m at t equals 0. If you simulate these on the computer, you give some m, glucose begins to rise. Because glucose rises, insulin begins to rise. Because insulin rises, removal of glucose rises, and glucose goes down. So that's why you have a rise and a fall. That's what you can do that in the computer, and you will. But I want to, let's use the tools that we learned in the leptin lecture to graphically see what's going on here, right? So let's use the tools we already learned, because you're now equipped to understand these two equations and two unknowns. How? We just need some space here to write things down. Let's do it here. We're going to use the phase portrait approach. So as you remember, phase portrait is a plot where you plot the important things. We used food and fat in the lecture. Now we're going to use glucose and insulin, the two variables. And by the way, this model was developed in the 1970s and has become a very important, it's called the minimal model. And it's become very important because in clinical practice, it helped define ways to define things like insulin resistance or insulin sensitivity. And so it's used clinically to help doctors understand what's going on with a person and researchers. And so this model has been calibrated in the 1970s by experiments. For example, you give an injection, IV infusia injection of glucose, let's say keep glucose level constant, and then measure insulin. Or you keep insulin constant and measure glucose in people, and you let it reach steady state, which maybe takes an hour or so. And that's how this model was calibrated. So very precise experiments. And so let's do those. You remember we had the diet line and the appetite line. Let's do the same. So how do you do that? What you do is, in order to get those lines, is you say like this. Let's imagine now that I'm keeping glucose constant by an injection, 5 millimolar, 6 millimolar, 7 millimolar, and I wait for insulin to reach steady state, and I plot how much insulin I get. So it's like the insulin secretion capacity of the body. In order to do that, so what's going to happen is I'm going to get an increasing curve. The more glucose I put, and the curve is going to look like this f of g, this function of more glucose, more insulin. So it's going to look something like this. This line is insulin at fixed glucose level. How do I get this line? I say I keep glucose fixed and I want insulin to reach steady state. So I say this is 0. This line is the line where the I dt equals 0, no change anymore. If the I dt equals 0, this line, to get I move it over here and divide by gamma. So this line is QB over gamma f of g. So I get one line. Now the other line, I do the same thing for glucose. What do? I say I'm going to now give you a fixed amount of insulin in your blood and measure how much glucose we have. So this glucose, I set glucose now to 0, and I get the other line. So that's our trick. This is called null lines, which if you have two equations, you'll have two null lines. One null line for d I dt equals 0, the other null line for dg dt equals 0. That's how you analyze these equations. Very, very simple. So if dg dt equals 0, m equals SIG, right? Because I move this SIG. And therefore, I equals M over SG. That's a line which looks like this. The more insulin I have, the less glucose I have, because insulin draws out glucose. So it looks like a hyperbola that looks like this. Right? And so this is glucose at fixed insulin. And when we want to understand the entire feedback loop, we just unleash it. And we ask, when does it reach a state where we have glucose level that gives you an insulin level that gives you that glucose level? And that's where those lines intersect. When do two null lines intersect? Null lines intersect at the fixed point. So this feedback loop has no choice but at steady state to reach a point where both the GDT is 0 and the IDT equals 0. That's the definition of fixed point, nothing changes. And when does that happen? When those two lines intersect. One line tells you the GDT equals 0, the other one the IDT equals 0. And when they intersect, they're both. That's the one point where they're both. And that's why we're interested in this point. And this point should be our 5 millimolar set point. Right? That's how this feedback works. Very similar to the fat insulin. Questions? Does the basal metabolic rate go higher after a meal? So basal metabolic rate, does it go higher after a meal? I don't know, but it's not a major way for removing glucose from the blood. And usually basal metabolic rate you measure basically over 24 hours and average it. So I'm not sure about that. Shouldn't this function be segmented? Yeah, this function here, I think you mean, should be segmented. I'm not sure what you mean, but below 5 millimolar, insulin secretion is very low, and above 5 millimolar, it rises, and then it reaches saturation. Everything in biology eventually reaches saturation. So that is, so insulin removal will be faster under physical activity. Is insulin removal faster under physical activity? I wonder why you say that. It's maybe because the blood is, when the heartbeat is faster or something like that. That's not a very commonly thought about effect. Okay, time delays. There's some time delays that are small compared to the hour time scale of glucose removal. So I ignored some time. So for example, if once insulin made, it takes about a minute to reach the muscle. So it's very interesting to think that a blood vessel takes about a minute to go through the entire circulation from the heart back to the heart. That's how fast your blood flows. So it takes about a minute for insulin to reach its target cells, but we ignore that in equations like this because it's slow. When you take it into account, it can explain some oscillatory phenomenon in glucose that happen on the scale of minutes that have been studied, kind of definitely. What can you repeat? What is K in the F of G? Yeah, the K here is the halfway point. So all these functions, if they go between 0 and 1, they reach 1/2 at K, 8 millimolar. And I say F of G goes between 0 and 1 because Q is the max insulin production per beta cell. So when FG equals 1, then production is Q times B. By the way, blood volume also factors in. Insulin is in units of concentration, and when you make a certain amount of insulin molecules, they get diluted in your blood volume. So when you're growing up as a kid, your blood volume keeps growing. And when you're pregnant, blood volume goes by 50%. And still, glucose is still at 5 millimolar. So how can the body know what the blood volume is? We're going to see that it's not so simple to understand that. Where does this equation know where the blood volume is? Because higher blood volume makes this Q effectively smaller because it's the number of molecules divided by blood volume. So how does the body know about that? That's something we're going to understand. Okay, so this feedback loop gives you a set point. Is there other feedback loops that connect glucose removal with physical activity? There are, for sure. So for example, maybe I should say right now, when you have physical activity, okay, the body knows the muscles need more glucose. And that's a great example for what I was about to discuss next, this parameter S. When you exercise, S grows. What does that mean? Insulin sensitivity grows. What does that mean? Each unit of insulin is more effective in removing glucose. And shall I just go to that? Oh, okay. So that's a way the body can use this insulin sensitivity, S, as a key parameter to control where the glucose is going. So if it's going, let's say, to the brain, primarily, you make S small. But if you want it to go into the muscle, you make S big. And that's, the body has ways to do that. I already said before, when pregnancy, you want glucose to go to the fetus. And so you make S small. So it doesn't go into the muscle and fat, it goes straight to the fetus. It stays in the blood, in other words. Yeah. When you have infection and you want, immune system needs glucose, you make S small. So insulin is less effective at removing glucose. Glucose stays in the blood, goes to the white blood cells that are fighting the virus and the bacteria. So S, insulin sensitivity, is a knob that controls allocation of glucose in the body. It's a great physiological knob. However, it's also a curse because okay, let's see where we are. We wrote the model, 2 equations and 2 unknowns, G and I. We talked about the half-life of glucose. We talked about the Hill function. We did the phase portrait. And now I'm talking about insulin resistance. Low S is called insulin resistance. The resistance. Just like there was leptin resistance caused a problem for obesity, insulin resistance, which means not the body tuning the knob according to needs, but chronically high insulin resistance. It means over a long time, S is small. That's one of the causes of diabetes because insulin is not working. And insulin resistance is found in all obese people. People with obesity have insulin resistance. And one reason for that is that the obesity is associated with inflammation, and the body thinks there's inflammation and therefore diverts glucose to the blood, even though this inflammation is caused by the obesity. And another reason is when obesity, the fat cells are so full of fat, they stop taking up fat, and this fat accumulates in muscle cells, in the liver, you get fatty liver. And when muscle cells see fat inside them and the liver, they have mechanisms that make them insulin resistant. That is to say, the insulin isn't as effective in getting those transporters to the cell surface. And so it's like they're saying the body is now using fat as an energy source, and I'm going to keep glucose in the blood for the brain, etc. And it's, again, an evolved mechanism, but it causes problems in obesity because we're not designed to be obese. We're not designed to have chronic insulin resistance all the time, and that's a big problem. So this parameter S, let's analyze what it does, okay? So let's analyze what happens in insulin resistance using our model. Let's take a nice deep sigh of relief. We're not just working here to analyze this model, we're working to see what happens when you have important problems like insulin resistance, right? Or as a knob, right? Okay, so what happens when we change S? Let's say we reduce S by a factor of 10 or something. That's like insulin resistance. What's going to happen? So we take a look at these knock lines and we ask, does S appear in this knock line? It doesn't. So it stays the same. Does S appear in this knock line? It does. When we reduce S, insulin isn't effective, and of course, glucose levels rise. So what does this reducing S shifts this whole curve? It shifts this whole curve like this. And therefore, we have a new fixed point, right? Insulin resistance. let's say S here went down. Okay. So what insulin resistance does is it increases insulin. So when you see a person with more insulin, you know they have insulin resistance. And it increases glucose, let's say from 5 millimolar to much more, maybe 10 millimolar. Bad, okay? So insulin resistance, of course, it's good if you're now facing an inflammation and you want to increase blood glucose for a while, or you're exercising. Exercising increases S and you shift down here, right? But for a while. But if you have chronic insulin resistance, this means you expect to have high glucose. But this creates a paradox because, however, most obese people have 5 millimolar and insulin resistance. So why is this a paradox? If this model is correct, they have insulin resistance and they should have 10 millimolar or something. But in fact, they have 5 millimolar. See what I'm saying? That's a paradox. This model seems to work when you think about it in words. But when you challenge it with the observation that the vast majority of people with obesity don't have diabetes, they have normal glycemia, normal glucose, maybe they have high insulin, I'll tell you, great. They do have high insulin, but their glucose is normal. Okay? So they have insulin resistance. And unlike what this model predicts, they don't have high glucose. They have normal glucose. So there's something else important going on that helps the body compensate for changes in insulin resistance. And another phenomenon we can imagine is what happens, for example, if, as I said before, a child is growing up or there's pregnancy. Suddenly blood volume changes. And so the amount of insulin in the blood drops because blood volume normalizes this production rate. So insulin gets diluted more. That's like saying that when we have growing up, blood volume increases, it's dropping the insulin line. We have less insulin at a given level of glucose. And again, glucose should rise. But that's not observed. Kids don't have hyperglycemia. Most pregnant women don't have hyperglycemia. Of course, there's a risk for diabetes-induced pregnancy. That's why pregnant women take the glucose tolerance test. And then some fraction of women, by the way, that predicts diabetes later on. And we can try to explain and understand it. But most people, blood volume changes and glucose stays the same. So that's another paradox. In fact, any parameter here, liver production, et cetera, that changes is going to shift these alkalines. That's fine in the weight set point because people do change. But in the glucose set point, they don't, unless something disease-like happens, which is diabetes. So we have a paradox here. We have a model, the minimal model, the standard model, but we have the phase portrait, but it doesn't explain the fact that insulin resistance doesn't automatically mean high glucose levels. In fact, for most people with insulin resistance, there's normal glucose levels. How does that work? What is changing here to compensate? What is going on? This will lead us to an incredible world of, first of all, understanding a compensation mechanism that works in all hormone circuits. And from this compensation mechanism, we'll understand why there's type 2 diabetes. And then we'll understand why there's type 1 diabetes, why the body attacks itself. And this will open up new principles that are beautiful to watch. So the take-home message from this lesson is that insulin glucose circuit keeps very tight homeostasis. The standard model explains this homeostasis kind of in words, but doesn't explain a well-known phenomenon in which people with obesity and insulin resistance have normal glucose. So we have the utility of understanding equations, and that opens up new questions and requiring new explanations. So let's take a nice deep sigh of relief. Those of you that want to ask some questions face-to-face, please stay online. And the rest of you, And I'll see you next week when we continue with insulin and glucose. Have a sweet week.